After having a few videos where we introduce three-phase system, delta and Y networks, we actually want to consider how to analyze these networks. So for that, we're going to consider a Y to Y network where we have a line impedance of 1 plus J1 ohms, and then we have an impedance per line for the load equal to 24 plus J19 ohms. We're going to say that VAN is equal to 120 volts, the phase angle of 30 degrees. And what we want to do is find the line voltage and the line currents for all of our lines. We're going to assume a positive sequence. So there's a lot going on in this problem, and that's why we needed a few videos to really introduce everything. So if we just look at our circuit, we can define VAN, our line impedance per line, and then our load impedance per line. And because we're balanced, we can just say that Z1 is equal to ZY, and it follows for Z2 and Z3. So what we're going to do is simply consider line A, where we have that VAN voltage, we have some line impedance, and then we have some load impedance. And the current going through this line is going to be equal to IAN, because both of these ends are connected to that neutral wire. So we can simply say that IAN is equal to 120 volts with a phase angle of 30 divided by 25 plus J20. And with a little bit of math, we simply say that that's equal to approximately 3.75 amps with a phase angle of minus 8.66 degrees. Now, because we are positively sequenced in this three-phase network, we know the phase relation between IBN and ICN. And from the last video, we know we have this relation for Y networks for the line and phase voltages and then the line and phase currents. So we can simply plug in for VAB as the square root of 3 times that phase voltage, which is going to be equal to 207.8 volts with a phase angle of 60 degrees. Again, we can shift by 120 degrees to get VBC and VCA. And we know that the line currents are equal to the phase currents. So if we wanted to find the voltage over the load, what we would do is take the phase current IA, multiply that by Z1 or ZY in this case, and we would get 114.79 volts with the phase angle of 29.71 degrees. And if we wanted the line-to-line voltage over that load, a little bit weird of a notation because we have Z1 and Z2. Seems odd, bear with me. We simply get square root of 3 times VZ1 with a phase angle of 30 degrees, or 198.82 volts with a phase angle of 59.71 degrees. Now, for a delta-delta network, or a Y-delta network, or a delta-to-Y network, you could try KVL or KCL. It's going to be difficult. It's not going to be easy at all. But if you convert to a Y-Y network, the analysis gets really easy because you have this neutral wire where you can independently look at each phase. So it gets easy. You just need to know how to convert between delta and Ys for the loads and the voltages. We did that in a previous video. We showed how that's possible. So anything that's not a YY network, convert to a YY network. And then find your values, convert them back. So if we had something where we had a line voltage VAB equal to 330 volts with a phase angle of 0 degrees, and we had some Z delta of 20 minus J15, we could convert to a phase voltage by that square root of 3, then we get a phase angle of minus 30 degrees, and then we can get ZY simply by Z delta divided by 3. So then our circuit looks something like this, and we can solve for the line current IAN. And then once we do this calculation and find out what this value is, we can simply convert back to the line current simply by square root of 3, and then minus 30 degrees for the phase angle. Shift by 120 degrees for IBC and ICA, and then you get all your values. So it's a little bit of work, but it's a lot easier than trying to deal with a delta to delta system or delta to Y.